All right. So molar concentration. What do you mean by molar concentration first? This is where we left off yesterday. So molar concentration noted.
Molar concentration, yeah, it's basically conductivity per one, like conductivity upon concentration. Concentration standing for 1 mole, like 1 molar conductivity, something like that.
My bad. I've been saying concentration. This is supposed to be molar conductivity. Sunday mornings are not.
An ideal time for classes? Yeah, we know that, miss. Thank you. Good morning.
But we'll get there.
6 more months, then I won't have any classes, only college to worry about.
6 more months, huh? Right.
Miss, I have a calendar and I cross out dates so that, I feel good that, days are getting over and I'm going to go to college in 6 months.
Nice. Okay. All right. So molar conductivity is conductivity per unit concentration. So now we're going to talk about the variation of conductance and conductivity with respect to concentration. Okay. So overall, what do you think? Like, how would concentration affect conductivity and conductance?
Decrease in concentration would decrease the conductivity.
Absolutely. So conductivity and conductance both.
Yeah.
Yeah. So conductivity.
Because the number of ions carrying the current would reduce.
Yes.
In a unit volume solution. So
exactly right. It's directly proportional to the concentration, because more concentration means more number of ions available for carrying the charge, carrying the current. Okay. So it's directly proportional because it basically depends, like, as the charge carrying conductor, you can say charge, or you can say current carrying ions increases. Yeah. So if concentration goes up, conductivity goes up because the number of ions increases. And if concentration goes down, the conductivity, conductance goes down because the number of ions decreases. That's directly related to that part of it. Now, the nature of electrolyte is going to, like, broadly speaking, yeah, this is the thing, but how it varies, like, it is directly proportional. Is it going to be a straight line, or is it exponential? Is it logarithmic? So that variance is what changes when it comes to, strong and weak electrolytes. Okay. So usually for standardized situations, like for example, when we're doing resistivity or even conductivity, we take it like for unit length, unit cross-section area in those terms, right? So for molar conductivity as well, like first conductance G is equal to kappa, like conductivity into A by L. Right? So if you're taking let's say when length is equal to 1. So if you're taking for unit meter like 1 unit, like 1 meter, 1 centimeter, what will happen to the volume?
Ma'am, I'm not sure I understood what you were getting at.
So like, let's say you have like a column of electrolyte. So suppose the length is equal to 1.
Miss, so 1 second. It is kappa A by L. L is equal to 1.
Yeah.
And A will be equal to V.
A equal to V, right? See, what is the formula for volume? Volume is like any volume.
Area into length.
Yeah, area of the cross section into length, right? So if you're considering length as unit, if it's unit length column, then volume will be equal to area.
Yes.
And this is the volume, like again, because we are considering all unit concentration, this is the volume containing 1 mole of the electrolyte. Okay, because we have taken concentration 1 mole, and in a situation A equal to V, where this volume is the volume that contains 1 mole of the electrolyte. So this in molar conductivity value, this we can also write it as, okay. Should I write Nietzsche or should I go to the next page?
Miss, you can continue down.
So lambda m is equal to kappa into the concentration. Now concentration contains 1 mole of electrolyte, so this we can also write it as K into upon 1 mole upon volume, because that is the concentration, number of moles of volume. So in that mathematics, this becomes conductivity into volume. Let me know when you're noting it.
Ma'am, could you explain the last formula one more time?
So molar conductivity is the conductivity per unit concentration. Now concentration is basically number of moles per unit volume of the substance, right? Of the solution. We took 1 mole of the electrolyte, and we said that 1 mole of electrolyte is contained in V volume of the electrolyte solution. So I've just substituted it there. So concentration ki jagah, I've put it as 1 upon V. Yeah.
Okay, ma'am.
So from this, what we can see is that the molar conductivity is directly proportional to the volume. And that means that if we increase volume, the molar conductivity is also going to increase. So if you keep on increasing the volume like so much, like you took 1 mole of, say, I don't know, acetic acid or something, and then you put that in like 10 liters of water, then volume is a lot more than the, like, you basically diluted it to almost to infinity, right? So at infinite dilution, that's what we call infinite dilution, when the volume is like so large that it might as well be infinity, considering the values. So at
can you go back for a minute, please?
Oh, sure. So infinite dilute part, I'll just come in 2 minutes. I'll be right back. Note it down.
Done now.
So at infinite dilution, like when you dilute it almost like a really large value, it might as well be infinity. The molar conductivity reaches, like lambda m reaches a limiting value. So even though you see that there's a direct proportionality there, it keeps on increasing. And at one point it reaches like a maximum value and it stops there. It doesn't increase to infinity. So that limiting value is called limiting molar conductivity. So that is called limiting molar conductivity. And it's denoted by lambda m naught.
Ma'am, it's a special value for at, like it's a special case only at infinite dilution, right?
Yeah.
Okay.
So at infinite dilution, it doesn't go beyond that certain value. So that maximum value is the limiting. So it's in the name, like it limits, you know, how much the conductivity can be. That is the maximum extent to which it can go. And that's like a constant value at a particular temperature for each electrolyte. Like you take HCl at infinite dilution, acetic acid at infinite dilution, ammonium chloride at infinite dilution. That way, it's a property of that. Okay. All right. So now we look at. Yeah.
Oh shit! I forgot what I want to ask. Sorry.
Okay. Ask when you remember it. So now we'll look at variation of molar conductivity, like general molar conductivity, like mathematically. We said it's directly proportional, but how exactly? So first case, we talk about strong electrolytes. So again, like these equations have been found out like experimentally by, like incrementally increasing and like figuring it out. So the variation for strong electrolytes looks like this. So molar conductivity is equal to lambda m naught minus area into root concentration. So it varies according to the root of concentration. Yeah. And this has a specific name. What is it called?
Miss, can you repeat the formula or whatever?
This formula should be generic, right? Why is it under strong electrolytes?
Yeah.
Okay, what is the difference between strong electrolytes and weak electrolytes?
Amount of dissociation.
Amount of
degree of dissociation.
Correct. So if I take 1 m HCl and 1 m acetic acid, will I have like comparable number of ions in both the cases?
No, you won't.
So will the conductivity be same in both the cases?
No, it won't be.
Right. So that is the reason.
So you'll alter this formula for weak electrolytes as well.
Yes. So for weak electrolytes, you need to take into consideration the degree of dissociation.
It is negative root C.
Negative किधर? This is just negative root के बाहर है.
Why na? Negative is, there is a negative, right?
A minus negative.
A minus root C.
Yeah. Is it not visible? What's going on? क्या हो रहा है?
Miss, the negative is, very, it's joined to this root. So,
A minus root C नहीं. Like A root C, A into root C. The negative is only here.
Okay.
So it is not, it is A into root C, right?
Yeah. Let me just like write it properly.
Okay.
Yeah. This equation, so this is called the Huckel, and there's one more person, Onseger equation.
Why couldn't scientists have easy names? I mean, seriously, every scientist we know in chemistry has the weirdest name possible.
Not every scientist is Indian. They're Greek and all, right? That's why they're weird names.
Like imagine if you come across, if somebody else comes across Ruparelia equation. They're going to feel the same.
No. It has to be either named by me, like my name, or some other name, not via my name. And I'm not going to find out any equation because I'm not going into chemistry. So,
Yeah, but just for,
For
compare.
the sake of imagination, Rithi, please.
I don't have the liberty to even imagine this.
Okay, so is equation में what all are the variables, things that vary?
Limiting molar conductivity?
Limiting molar conductivity is a variable,
No, that will remain constant.
a constant. So which ones are the variables? What can you change? Like what is the
Concentration.
concentration is a variable, and what other things can
Area.
you won't be like every time you won't be taking like a different container, right? So area of cross section be kept constant for a particular. So based on the concentration, what other quantity is changing here?
Delta M.
See that?
Delta nahi hai. This is lambda, capital lambda. If it's a triangle,
Sorry.
it's delta. Okay.
Lambda M.
Molar conductivity. So these two are the variables. So what can you say about, like, if I draw a graph, if I plot a graph between lambda m and root c, what kind of a shape will I get?
Exponential, I think.
Math people, like what equation, is it linear, is it quadratic? I'm talking about lambda versus lambda m versus root c. Lambda m versus root c. Like just put variables in their place and see what it looks like. If this is y equal to random constant, minus a is also another random constant, into root c is another variable. What kind of graph will this equation make?
It'll be a normal linear graph.
The linear equation, y equal to mx plus c. Okay. So 1-to-1 relation here. This is power 1, root c is also power 1. So it's going to be a straight line. So for this straight line, can you figure out what is the slope, what is the intercept?
Ma'am, the intercept is lambda naught, right? Lambda
Lambda
and
dot
naught.
m.
Sorry.
Yes, absolutely. And slope is going to be?
The area.
Area? Area of cross section, correct. Not the graph area. That is absolutely right.
No, yeah, the area of cross section. I was saying according to the formula given.
Yeah, absolutely. So this is what the graph is going to look like, taking root of concentration on the x-axis and lambda m on the y-axis. This maximum point, this point represents lambda m naught, the limiting molar concentration, and slope of this line is going to be equal to minus a or minus a. Is going to be equal to a. That is the area of cross section. Cool. So this is specifically for strong electrolytes. So strong electrolytes, do you know what are some of the strong electrolytes? What will you apply this to?
HCl, H2SO4.
H2SO4, yes. What are
NaOH,
NaOH? Yes.
KCl,
KCl, things that can dissociate easily. Think of strong base, strong acid salts. KOH. Calcium chloride as well. Yeah. Na2SO4. These are strong electrolytes. Clear. And after this, we will discuss for weak electrolytes. Let me know when you guys are ready, and then we'll go ahead with this.
Ma'am,
Yeah.
what was C?
C is concentration. C is always concentration. This you can ignore. This is if you want, you can note it down to see how this is a straight line, but otherwise whatever is in pink is just for understanding. So lambda m is molar conductivity.
Miss, 1 minute, I'm still writing.
Yeah.
Done, ma'am.
Yeah. Ali is also done. Ansh and Shantanu, should we go to the next part?
Give me a minute.
Yes, ma'am.
So we'll discuss the weak electrolyte part in a bit. So before that, we'll talk about the Kolrash Law, because that is also applicable to strong electrolytes only. We'll discuss that quickly, and then we'll go to the weak electrolytes.
Miss, can't we finish weak electrolytes, because then it becomes easy for us to write, at least for me, strong electrolytes and weak electrolytes, and then the entire new law. So notes will be easier.
Yeah, I see where you're coming from, but Kolrash Law will be talking only for strong electrolytes. So I figured let's keep all the things related to strong electrolytes together, and then we'll go to the weak.
Okay, thank you.
Done, ma'am.
Cool. All right. So Kolrash Law is like, the application of it is pretty easy. The spelling is a little, it's cool. One word, right? Kolrash Law. So this is also called Kolrash Law of independent migration of ions. Okay, so what Kolrash Law says, like the statement is that the limiting molar conductivity of an electrolyte is the sum of the individual contributions of the cation and the anion of the electrolyte. So let's say if you have for an electrolyte AB, like AB is like could be KCl, NaCl, whatever, cation A, anion B. So specifically, this needs to be a strong electrolyte. Okay, it's applicable for strong electrolytes. What Kolrash said mathematically is that the limiting molar conductivity of AB as an electrolyte is equal to the individual contributions of the cation and anion. So this is equal to the individual contribution for conductivity of A plus and the contribution of B minus, the cation and the anion. Okay. So if I had to write the statement, limiting, so this is the statement that he gave. So it's basically this equation written in words. So the limiting molar conductivity of an electrolyte so in this case, we have taken it electrolyte AB is the sum of, so we are adding two things, these two things. The individual contributions the sum of the individual contributions of the cation and the anion. Okay, so that's it, like whatever is written here. So molar conductivity of the electrolyte is equal to the molar conductivity of the cation plus the molar conductivity of the anion. So if we have to consider generalized form, like this is in the case if it is straightforward AB. But what if you had something like Na2SO4 or CaCl2, which is made up of multiple ions? So the generalized form is, you can write it like this. So this is the one you'll use in your questions. So limiting molar conductivity, let's say the electrolyte is, you have cations which are new number of cations and new number of anions. So that will be equal to mu into the lambda, the conductivity contributed by cations plus mu into the conductivity contributed by anions. So basically, for example, if you were to figure out the molar conductivity of CaCl2, so this will be equal to, there is one atom of calcium, so it's lambda naught into Ca2 plus, and there's two atoms or ions of Cl2, so it's 2 into lambda naught of Cl minus. This is how you'll apply it. So this law also, Kolrash was able to give this law again through experimentation. So he was looking at the lambda naught values for like a lot of strong electrolytes, and he observed, okay, this is how the numbers were. Okay, so this is the case. Like again, it was through experimentation and observation. Like if you compared KCl and NaCl versus, again, KCl and I don't know, K2SO4 or something, the value by which their conductivities differed was pretty constant. Like that's how he could figure out that, oh, this is the amount by which it varied. So that must be the case.
Done, ma'am.
Done? Okay. Right. Ansh and Shantanu. Mitali, are you back yet?
Yes, ma'am. Could you just give me like 2 minutes to note it down?
Yeah, sure. Go ahead. Yeah, note this down. I will get myself some coffee in the meantime.
Miss, I'll be back in a minute.
Okay. Electrolytes. All right. Coming to weak electrolytes. I don't think there's any equation given for weak electrolytes as such, but the variation is slightly more complex. Okay. So in the case of weak electrolytes, it is not as straightforward because there is no complete dissociation. But what does happen is that, okay, so at lower concentration, which means that dilution is pretty high. Like think of 1-2 drops in a whole 1 liter bottle full of solid. So what did you learn? Like what happens at infinite dilution? Or do you guys remember the whole concept of dissociation? Like what happens to the or what is the dissociation like at extremely low concentrations?
There is some value, right? It's like lower than 1. I don't know.
Are you going to find like a relatively higher amount of dissociation? Like is there a
At
way?
lower concentrations, no, ma'am.
No.
Could you repeat? Yeah.
Lower concentration matlab at high dilution. Like low concentration matlab it is extremely dilute.
So
About
so in terms of that, at lower concentrations we'll have high dissociation, and at higher concentration we'll have low dissociation.
So what can you say about the conductivity in that case? Like if the
Conductivity is high when the concentration is low.
Yes. So again, like the overall direction broadly is same as
parabolic
seen for strong electrolytes, except it's more exaggerated. You can think of it that way. So
ma'am, I have a doubt.
Like that, you know, like one, like that.
It's gonna look something like this. Okay. So at low concentration, because of high dissociation, it's gonna have like extremely high values of what do you call this? Conductivity. And as you said, high concentration, low dissociation, and so it's gonna look something like this.
Ma'am, I have a question.
Yeah.
So could you go back to the strong electrolyte wala graph? So ma'am, in the NCRT, what they've done is they haven't touched the line all the way to the origin. Even if it's for the y-axis, they haven't done that.
That's actually right. Like technically, that's right, because concentration, when it is 0, then there's no question of conductivity. So it should be slightly.
Yeah, so that's why she was like, you can extrapolate it, but it can never touch 0, because if it touches 0, then it's wrong.
That is correct. You can't do that, because at 0 concentration, obviously, there is not going to be any conductivity. That does not make sense. She's right. But yeah, at infinite dilution, this particular value is going to be equal to lambda n. Right? The same thing is in the case of this also. Like you can extrapolate it. It's going to go parallel to the y-axis, but it's never going to touch. It's going to be like that. And this also, like as you increase the concentration, it goes parallel to the x-axis, but yeah, it's never going to touch there. So yeah, this is the shape of the graph for weak electrolytes. Also, it has been found out that again, there is no derivation as such for this, but it's been found out that the degree of dissociation is also equal to lambda m upon the limiting molar conductivity, lambda naught m. Okay. So degree of dissociation alpha. I think dissociation has 2 S's.
Yes, ma'am.
Yeah. Now going back to your grade 11 stuff, do you remember what Ka, Kb, like how that relates to, like what is the expression, what is the value of Ka? Do you remember the formula?
Nope.
No? Okay, we'll do a quick refresher here. It's pretty easy. So let's say you have acetic acid or a weak acid, AH, gives H plus and A minus. So concentration at T equal to 0, you've taken C amount of it, there was 0 and 0.
Oh, so same thing.
Yeah.
Huh.
After a while, if the degree of dissociation was alpha, so C alpha has dissociated, you get like this much has dissociated, which means that there is C into 1 minus alpha remaining of this, C alpha of this, and C alpha of this. Now, can you form the expression for Ka? It is equilibrium constant. So again, same.
So C alpha into C alpha
Mhm.
upon C by 1 minus alpha.
1 minus alpha.
So C will get cancelled. So C alpha square by 1 by alpha.
1 minus alpha.
1 minus alpha, sorry.
So here also, like Ka is going to be equal to C alpha square by 1 minus alpha. So because alpha is equal to lambda m by lambda naught m, you can substitute that in here and then figure out the dissociation constant. So if at all you have to find the dissociation constant, this is one method that you can use based on the conductivity.
Oh. Yeah, that's what I just derived that and now I'm looking at whether it's right or wrong. No, it's right. That's what I got.
That's good. Good practice in math. Okay. Let's practice some questions of this. After this, we have electrolysis part remaining. That is very, very easy. That's more of, you need to know stoichiometry. Like once you know stoichiometry, it's just apply Faraday's law to it. You get it. Okay. So Ansh and Shantanu, you guys have noted this down?
Yes, ma'am.
Done, ma'am.
Important bit. This, if you want a refresher, like if you don't remember the grade 11 stuff, you can
A minute.
derivation side mein. Yeah. Okay, we'll do some like 2 example problems and then we'll go on to
Ma'am, so based on this or like based on what we've done so far?
all of concentration related stuff.
Okay.
So molar conductivity and also molar conductivity, actually all of you have practice, no? That I can skip, I think. Yeah, then we'll do it based on this, what do you call it? Yeah, molar conductivity, Kolrash Law and all that stuff. Degree of dissociation. All right.
Ma'am, for the MCQs, could you present the screen if we're doing MCQ, because I don't have the PDF.
Yeah, sure, will do.
PDF ma'am sent on WhatsApp.
Yeah, but then if she presents or like much easier.
It'll be easy, like all of you will have the same source. Okay.
What was the x-axis of the graph?
X-axis was root concentration, root of concentration, C power 1.
Okay.
Yeah. Okay. So calculate the limiting.
You have to solve example 2.
Yeah. For acetic acid, given that HCl का limiting molar conductivity पता है, NaCl का पता है, and sodium acetate का पता है. Yeah. This kind of problem, like if it's given in this format, you can figure out, use Kolrash Law. So
Ma'am, but if we use Kolrash Law, wouldn't it be, we'll have to remove, because we're finding it for acetic acid, we'll have to take the third one.
yeah, form equations for each one. So if you want to find for acetic acid, you need to know what is lambda naught for acetate ion.
Yeah, that
And
we'll find from the third.
You need to
equation,
figure out
like
the
third one.
lambda naught for H plus.
So ma'am, why do we need, if we don't use the second equation, that's all right, right?
You will need to use the second equation because इसमें 91 includes acetate ion plus Na plus. So you need to remove Na plus. Where will you get that from? You'll get that from NaCl.
Oh, okay.
So these kind of questions, right? Each one, write this as lambda naught H plus and lambda naught Cl minus. This is going to be lambda naught Na plus and lambda naught Cl minus. This is going to be acetate ion plus Na plus. So once you have the equations, you have to manipulate
This
it.
is the answer 391 SCM square per mole.
Yeah, I remember seeing something like that. Yeah. So these kind of questions, once you have these equations, you need to add or subtract them, manipulate them somehow so that you get this on one side, and then whatever numerical values you have on adding, subtracting, that will give you the value of this.
Yes, ma'am, got it.
Got it? Okay. Shantanu, you guys got it solving it?
Got it.
Okay.
Yes.
If you want me to do any one problem on the board, let me know, like as an example. Otherwise,
Ma'am, basically we'll just substitute it here and there in order to get the desired,
this equation.
yeah, this equation. Okay. Okay, ma'am.
Shantanu, Ansh, did you guys finish solving it or you're still calculating?
I'm done.
Done, Asha. Okay. Answer bhi mil gaya. Okay. Nice. Shantanu, what about you?
Can you solve it?
All right. Okay. I'll take it to the whiteboard. Huh? So you given that, can you guys tell me the value? Lambda HCl, how much was it given to be?
426.
426. The second one
91
NaCl was
minus
1.
126.
Second one was NaCl, right?
91. No, NaCl is 126.
It's 126, yeah.
Sodium acetate,
And CH3CONA is 91.
91, right? Okay. So we need to find what is lambda naught of CH3CO minus and lambda naught of H plus. This
So, ma'am,
yeah.
yeah, so for H plus, I substituted the Cl minus on that side. So it'll become 426 minus lambda naught Cl minus, right? Then same for the second one where lambda naught Na plus will be 126 minus lambda naught Cl minus.
Yes.
Then for the third one, in the place of lambda naught Na plus, I've substituted 126 minus lambda naught Cl minus. Minus lambda naught Cl minus. And then basically we'll find the answer, right?
Yeah.
Okay.
Yeah. So like you need to take one value, substitute it in another, eventually you need to
Yeah.
another way. So if you add these two, like we need CH3CO minus and H plus, right? So this has CH3CO minus, this has H plus. We have, then we'll get a Cl minus and a Na plus extra. So usko, we need to subtract this. Okay. So this, if we call this equation 1, equation 2, equation 3. So if we do equation 1 plus 2, this is gonna give us addition of these two minus, sorry, 1 plus minus equation 3, the middle equation. Then we can get rid of Na plus and Cl minus, which we don't need. So do that, and then you'll end up with CH3CO minus and H plus. So that would be 426 plus 91 minus 126. So whatever value you get here, that's your.
Yes, ma'am.
Yeah. Shantanu, did you get the hang of it?
Yes, ma'am, I understand.
This is like more mathematics or logic than chemistry. The chemistry, the only thing you need to know is like splitting this into ions. Look at example 3. So conductivity of this much concentration acetic acid is this much. Calculate the molar conductivity. This is pretty easy, you can do it directly. Now, if limiting molar conductivity of acetic acid is this much, then what would be its dissociation constant? So do you remember the relation between limiting molar conductivity and dissociation constant?
Lambda m naught is equal to, no, wait, we'll have to substitute it.
Oh, the
No,
formula
wait.
is even right here. So dissociation
Yeah,
constant
yeah.
lambda m.
So lambda m naught is lambda m by A. So dissociation constant.
Yeah.
Conductivity is given. So concentration and conductivity is given.
So
We have to calculate.
molar conductivity. Once you get the molar conductivity.
Ma'am, molar conductivity, so we can
conductivity I'm
simply do
getting
7.896 into 10 raised to minus 5 upon 2.41 into 10 raised to minus 5.
2.41 into 10 raised to the
Into
power
10 raised to 5. 5, sorry.
5, yeah, or 3.
1, 2, 3. Oh, 3, 3.
3
10 raised to 3.
minus 3.
How is it minus?
No, sorry,
Yeah.
3.
3, it'll be 3.
Sorry.
Anyway,
Yeah, after that we get the molar conductivity, right? Okay.
yes.
Molar conductivity, I got the value which is 32.77. Is it right?
Yeah, you are correct. Molar conductivity, you'll get somewhere around.
So then degree of dissociation will be molar conductivity upon lambda not m.
Yes.
So 32.77 by 390.5.
Yes.
That is equal to 8.4 into 10 raised to minus 2.
Is that what you got?
Yeah.
8 point something. Yes, that is correct. Exactly. Yeah.
Now
Guess
C alpha square by 1 minus alpha. So C is 0.00241 into 8.4 into 10 raised to minus 2 the whole square by 1 minus 0.084.
Yeah.
One 1.86 into 10 raised to minus 5.
Yes. Nice. And Shantanu, you guys also put your answer, say your answer as you're doing it.
I've got molar conductivity as 3.22 into 10 raised to minus 6.
3.2 into 10 raised to the power minus 6. Minus 6 because numerator may you have 10 power minus 5, denominator may you have 10 power minus 3. So those two will get cancelled and it will reduce.
It's not minus 3, right? It's 3.
Oh, this is molar, right? Huh. You need to convert this to centimeter cube.
Yeah.
The units. Okay. Yeah. I'll have to do this. I'll check here.
What we have to, so I calculated the molar conductivity.
Molar
Now what we have to
conductivity,
calculate is
just check the exponents, because molar conductivity you're supposed to get 32.76 directly. You get a really small value.
32.76. Oh. If I take minus 3, then I get 32 point, like I get the answer. But then it can't be minus 3.
No. Let me do this here. Let's convert this to mole per centimeter cube, 0.00241. This is mole per liter, right? So 1 liter is 10 power minus 3 meter cube. So mole upon 10 power minus 3 meter cube. If I convert this meter cube into centimeter cube, what will my exponent change as? 1 meter is 1000 centimeter, sorry, 100 centimeters. So this is going to be ten power minus 6 centimeter cube. So if this goes into the numerator, it's going to be 0.00241 into 10 power 6. So this is divided by Hmm. Ten power minus 6 nahi hoga. This is going to be will be 100. 1 meter is 100 centimeter. Mole power minus 3 is 10 power minus 6 centimeter cube. If that goes in the numerator, it's going to be 10 power 6. So that will turn into okay, got it. So you have 7.896 into 10 power minus 5 divided by 0.00241 into 10 power minus 6. No, this will be 10 power 6 because numerator mein aa gaya. Now this 10 power 6, if we get rid of the decimals, you get 2.41 into 10 cube. How is this working out? So molarity is this much. Mole per centimeter cube में convert करने के लिए they took it as 10 power minus 3. They just divided it by 1000. Okay. Conversion भी देखा. So 1 liter is, or 10 cube liter makes 1 meter cube, which means that 1 liter is 1000 centimeter cube. This is the conversion. So this 1000 goes into the numerator. Yeah. That's correct. So it won't reduce, it won't be 10 power minus 6, it will be 1000 centimeters. Right. Let me know when you guys are done with this problem. Jyoti is done. Once all of you are done, we'll look at the MCQ.
Yes, ma'am.
Yes, ma'am.
Yes. Okay. Yes, you are done, or yes, you will let me know.
I'm done.
Done. Okay. Ansh?
Okay.
Ansh Gupta, can we start doing the MCQs?
Yes, ma'am.
Okay. I'm skipping the first part of it, 24 tak, because that was like introduction. You were supposed to do that last week. So we'll start. Do you guys want to do from Nernst equation or only the...
Yes, ma'am. Can we do from Nernst equation?
Okay.
Nernst.
Okay, Nernst equation, like we're starting off with the basics. Look at question number 26. You're given 4 different versions of the equation. Which of these is correct?
send you the answers in chat, right?
Yeah, send the option number in chat.
Are you?
No,
No?
Dhriti is correct. Mitali, check your answer. C, you can straight away like ignore it because plus nahi hoga. D, also you can ignore because it's RHS should come first. So it's between A and B. Ansh, you got it correctly. So Shantanu, figure it out. And Mitali, so the only difference between A and B is यहाँ पे you given concentrations of the ion, यहाँ पे you
Oh, okay.
M.
Yeah, I didn't. That.
C. Yeah. Okay, Shantanu, I have not received your answer yet. Shantanu Dhageria, what's going on? Okay. Shantanu, you also did the same thing Mitali did. So M matlab, that's like solid metal. So uska concentration hamesha 1 hoga na. You always need to take the concentration of the ion, like jo bhi electrolyte mein. Okay, so that's one thing you need to be careful about. So iska answer hoga option A. Yeah. Got it, Shantanu?
Yes, ma'am.
Okay. Similar question given in a different form. Mark the correct Nernst equation for the given cell. So you're given the cell here, which should be the correct equation.
We are doing 27, right?
Yeah. Dhriti has already answered. Yes. Okay. Looks a little confusing, right? I'll just like, I wonder if this would help. Does this help with the clarity?
A little bit now.
Mitali has also sent awesome. Correct. Ansh and Shantanu, you guys. Ansh, you got it now. That is correct. Shantanu, just waiting for your answer. Whoa, okay. Shantanu, if this is the cell, right? Can you figure out what are the reactants and what would be the products? So Fe or Fe2 plus may say which one is the reactant, which is the product?
Fe is the reaction.
Fe is the reactant which is producing Fe2 plus, right? So Nernst equation में numerator में Fe होना चाहिए या Fe2 plus होना चाहिए?
Fe2 plus.
Plus होना चाहिए, right? So that leaves us with either A or C. Abhi in this half reaction,
It's C.
C should be the answer. Yeah. All right. Let's step it up. All of these are going to be, practice of this thing only. Do question number 30. You've written Nernst equation now. Now put values in it and apply it. So let's put a time aspect to it. It's 11:19, right? So how long will you guys take to do this? Logarithm karna hai, then calculate.
2 minutes.
2 minutes, okay. 11:21 tak try and finish it. Oh, this is a concentration cell. Oh, this is a good question. Concentration cell is something that we did not talk about, right? Did we?
No, miss, we have not done concentration.
Concentration cell, okay. So concentration cells are like a specific case, like a special case of cells. You can see that it's the same, like it's the same for oxidation and reduction half. It's the same thing, just different concentrations are used. You see that it is silver and silver nitrate. In the
Yes, ma'am.
reduction half also you have silver nitrate to silver. The only difference is that in the oxidation half, reduction half, you take different concentrations of the electrolyte. Those cells are concentration cells. What are
Ma'am,
the
but here, how do we figure out which are the reactants and which are the products?
simple? Like this is the cell, this is the equation, right? Always this reacts to give this. So Ag is getting converted to Ag plus. In this case, always Ag plus getting converted to Ag. So it's only the concentrations you need to take carefully.
Okay.
Standard. So one convention in concentration cells is that, like you can see that happening here also. The one with higher concentration is usually the cathode, and the one with lower concentration is usually the anode. Which makes sense, right? If there's a higher concentration of Ag plus, that's going to push the reaction in the other direction. Ag plus getting converted to Ag. Yeah. What's going on, Riti? Solving? Sorry. It's 11:22, right? Okay. I was thinking, how about I give you guys problems to do, like do 31 to 40 or something like that. And then we'll meet back in half an hour or something, how much ever time we take to do the problems. And then clarify all the doubts. How does that work? Instead of doing one by one at a time.
Miss, I'm doing the whatever working is to be done on the paper only.
Yeah.
That's okay, right?
You took printout of the PDF for Winnipeg.
Yeah.
Okay. Cool. So wherever you're doing, you can just scan that part because yeah.
So, ma'am, have you allotted the questions?
I'll check 1 second. Mitali, you already sent the answer, and that is the correct answer. Got it.
Thank you, ma'am. So we solve from what to what questions?
I'll let you know.
Oh, okay.
You guys remember the whole concept of like solubility product and all? Where to use it, what to use it, and what is the significant?
Ma'am, do you mind doing a recap?
Okay, sure.
Because that was probably the most trickiest part of equilibrium.
That was the last part, right?
Miss, I can't
Yeah.
see the screen. It's all black. Can you reshare?
It's so strange. And Dhriti, that happens on your system only, right? Like others were able to see it.
My system is old.
Hmm.
It's, on the verge of dying. I'm just stretching it for the next 6 months. Then I'll get a new laptop.
No, I'm trying to figure out because that happens every time I pause the screen. And I pause the screen because when I want to scroll upar ya niche to check like the next questions, I want the question to be still visible for you guys. So
Sorry.
that's the weird part. Yeah, but if the screen is going blank, like that basically defeats the purpose. All right. Once everybody's done with 30, I'll discuss 31 because that has stuff to do with like solubility product and all that.
Okay, ma'am.
The other questions.
Miss, my answer which I sent is wrong. Sorry.
Oh,
Yeah.
1126 go what you sent. So you'll be sending a different answer, is it?
Right now, I sent another answer.
Okay.
I mean, the value was the same, just the sign different.
Acha. That is like Shantanu also sent it abhi. Both of you are correct. Okay. So Ansh, yours is the only one remaining. Kya kar rahe ho? Like what's going on? Ansh Gupta. The sign is different. It's a different sign. You should get 0.0413. Okay. So the next question, standard reduction potential for Cu2 plus to Cu is plus 0.34 volts. What will be the reduction potential at pH equal to 40, given that Ksp of the solubility product of this is 1 into 10 power minus 90. So there are a few concepts in this question. So we'll deal with them one by one. So first thing is reduction potential, the standard reduction potential. What do you mean by the standard reduction potential?
Where H plus ion is converted to H2 gas in the presence of platinum electrode. Yeah.
Absolutely. So is that process going to be at cathode or anode?
Cathode.
That is going to be at cathode. Okay. So that is the at standard conditions, it is the standard reduction potential. But otherwise, whenever we talk about reduction potential, you can assume that it is basically the EMF when the cathode is this equation, H plus gives half H2 gas. Okay. So 1/2, like the reduction half of it is always going to be H plus to H2. And the oxidation half of it is going to be whatever you take. So in this case, it is Cu and Cu2 plus, that part of it. Okay. So standard reduction is this much. And when we say it is standard reduction, it is for like when the concentration of H plus is 1 molar. So when pH equal to 14, now what does this signify? Like, what do you understand by this equation? pH is equal to 14. Say what information are you getting?
Concentration of H plus ions.
Yeah. How much is the concentration of H plus ion?
14.
14 molar. pH is 14, right? So concentration of H plus is going to be? It's going to be 10 power minus 14. Remember,
10 power minus 14. Yes, sorry.
theta of anything is minus log of that thing. So reverse it, like if I'm removing P, that goes into 10 raised to the power that thing. Okay. So pH 14 matlab concentration of H plus is 10 power minus 14. And yeah, so based on that, you're given that solubility product of calcium hydroxide is this much, which means that, sorry, calcium, no, copper. Copper dissociates into Cu2 plus and OH minus. So because you know what is H plus ion concentration, use that to figure out concentration of OH minus ion concentration. And from the solubility product, you can figure out what is copper ion concentration. Just a refresher from last year's, what do you call, equilibrium chapter. So one, pH is basically minus logarithm of the concentration of H plus ions. And POH is basically the same thing, minus logarithm of OH minus ion concentration. So if you're given pH and you need to find out concentration of H plus, that will basically be equal to 1 into 10 raised to the power, whatever number the pH is. Similarly, same thing. You have to find out the concentration of OH minus, that's equal to 1 into 10 raised to the power minus whatever is the POH number. So if POH happened to be 8, then this is OH minus concentration is 10 raised to the power minus 8. Simple that way. The next thing, what is do you remember the quantity called Kw? So this is also called ionic product of water.
That is equal to 14, right?
Yes. So this is equal to concentration of H plus into concentration of OH minus. So for neutral water at standard condition, 10 power minus 7 into 10 power minus 7, that is equal to 10 power minus 14. This is the ionic product of water. Next, this particular case, you have solubility product KSP. So KSP is equal to, like if you have for any salt AABB, like yahan pe you had CuOH twice, right? So A is only 1, B is like 2. So if it's of the form AABB, then the solubility product of that salt is concentration of A plus raised to the power A, concentration of B minus raised to the power B. So in this particular case, like if you're considering for CuOH twice, 10 power minus 19, whatever value is given, is basically equal to Cu2 plus ka concentration into concentration of OH minus ka square. That's what it, like, that's the expression you need to know. Yeah. So these are like, yeah, quick things. Now, using this, will you be able to solve the equation? Like, if you want, you can make a quick note of this somewhere, like on the side or in your notes or on a post-it or somewhere. Make a note of this and then try solving that question. I'll give the like whatever is given, I'll write it over here, I'll give the information here. So question number 31, what is given is standard reduction potential for Cu. The standard reduction potential for Cu2 plus to Cu is plus 0.34 volts. What else is given? What will be the reduction potential at pH 14? We need to find it at pH equal to 14, given that Ksp of calcium hydroxide is equal to 1 into 10 raised to power minus 90. Okay, so this is the deal. So these are your given conditions. Using this, you need to find out the reduction potential at pH equal to 14.
Ma'am, when it says standard reduction potential, that means our cell representation will be Cu2 plus line Cu, and then the standard reduction potential ka representation, right?
Yeah.
Okay.
Essentially, what you need to get out of this is basically represents the E. So at standard condition of 0.34, you just need to find out at when the concentration has changed.
So we'll use the Nernst equation to get it right. Yeah, okay.
So to find, again, it is reduction potential, right? So Nernst equation में डालने के लिए you need to figure out H plus का value and Cu2 plus, these two concentration values.
Ma'am, pH is given, so we can find the H plus ka value. It's already given. Other than that,
Cu2 plus you need to find.
and other than that, Ksp of Cu that is given. But how will I find the Cu2 plus ka value?
This one. This particular.
Yeah, but like KSP is 1 into 10 raised to minus 19 is equal to A. That will be, I'm taking Cu2 plus and 2OH minus. Oh, using KW. Okay, no. Okay, got it. Oh, so we're using, ma'am, we're using
Another
every single equation.
Another
Wonderful.
correction. Uh, so H plus concentration, always when you're figuring out the reduction potential, right? It's always going to be 1.
I'm sorry, ma'am. Could you repeat that?
H plus concentration, when you're using it in an electrolyte, like for the reduction potential, this is always at unit concentration. So that's always going to be 1.
Okay.
So this pH is the concentration where copper is. So you have 2 half cells, right? So 1 half cell
Yes, ma'am.
is always you have an acid, and this is the H2 side of things. The other half cell is where you put your specific electrolyte. In this case, it's copper hydroxide. So the pH of this solution is 14, which does not change the concentration of H plus on this side. So this is always going to be at unit concentration, 1m.
Okay.
So when you apply it in Nernst equation, H plus concentration is going to be 1.
So, ma'am, when we use the ionic product of water wala equation, even there the H plus concentration will be 1.
No, because that you're applying to this side of the solution, which is not, you're not taking unit concentration, you put some copper hydroxide in it.
Okay. Ma'am, it's an MCQ, right? So could you show us the options?
Yeah. Scroll up.
Yes, ma'am, I got it.
You sending the answer?
Yes, ma'am.
Awesome, you got it right. Dhriti also sent it. Nice. Good stuff. So after this, I want to do a couple of electrolysis related questions. It's very easy because if I finish that off, you can basically practice the whole chapter. Like we can close it out and start a new one next time. Ansh and Shantanu, what's going on there? Did you get it? Are you still solving it? Are you stuck somewhere? क्या हो रहा है?
Solving it.
Solving, okay. Method तो आ गया ना? Like you're not stuck anywhere, right? Ansh, what about you?
I'm
Doing it, okay. Like if you're stuck somewhere, let me know. Otherwise, yeah, if it's just calculation and you're in the process of solving, yeah, continue. In the meantime, Thriti and Mitali, you guys look at question number 33.
Yes, ma'am.
Question number 32.
33. 32 seems to be incomplete because following half cell reaction bola hai, but
Yeah,
yeah. Do 33.
33.
Shantanu, no, that is not the correct answer. Can you send your working like quickly, like wherever you did the calculation? Can you just like click a picture and send it? I want to see how you did it. Oh, you also already got it. Okay, Ansh got it. 31 ka answer. Nice. So Shantanu, like, yeah, I just want to see your recording what happened because you didn't get the correct answer. Oh, okay. Now you sent it. Like, what happened? Like, where did you make the mistake?
No, I accidentally sent the wrong answer.
Acha. Okay.
Ma'am, 33.
33, like, it's okay. That's
Oh,
a
okay.
one. But I wanted you guys to do. So look at question number 68. Just read the question, see if you can solve it. I'll just be right back. Someone at the door. Okay.
Yes, ma'am. I am not sure.
Okay, let's do this. Okay. Okay. How long would it take? Oh, Triti has already solved it. Good. So how long would
Is
it
it
take
right?
to, I think so. I'll have to check. So how long would it take to deposit 50 grams of aluminium from an electrolytic cell containing Al2O3 using a current of 105 ampere? Okay, first of all, what is the reaction that is taking place in this scenario? So electrolytic cell containing Al2O3 matlab?
Electrolysis is taking place, right? Al2O3 will is the electrolyte, salt electrolyte, and it will dissociate into Al3 plus, 2Al3 plus, and 3O2 minus.
But what products are we getting out of this electrolysis?
Aluminium metal, because that's what it's asking us for, and oxygen gas.
Yeah. So balance out this equation. यहाँ पे 2 आएगा and that's 3. It will be 6Al and 3O2. Yeah. ठीक है. So okay. We need to deposit 50 grams of aluminium. Okay. So first of all, figure out how much, like if we are, how much electricity. So before going with the electricity part of it. So here we are we are using a current of 105 ampere and we are being asked, okay, how much time is it going to take? So how is like current and the charge, like what is that relationship between current, time and charge?
I is equal to Q by T.
Equal to Q by T, right? So if we send I amperes of current in T time, then Q amount of charge is what is flowing in that particular current. Now keep that aside. Now this current, whatever Q charge is flowing, is being used to reduce aluminium from Al3 plus to Al, right? So from this equation, if like what is the number of electrons that that is involved in this equation?
Number of electrons.
Yeah.
As in like
3 plus.
So Al will lose 3 electrons and oxygen will gain 2 electrons.
Huh? It's the other way around. No, you're getting aluminium metal. So Al3 plus is getting reduced to aluminium.
Oh, it will gain 3 electrons, sorry.
Yeah, it is gaining 3 electrons. So this 3 electrons, it is gaining from whatever current you're passing through. So to like how many electrons or how much current or let's say how much charge is required to get 1 mole of aluminium?
3 electrons.
3 electrons, right? 1 mole of aluminium matlab you need 3 moles of electrons. So that is equivalent to how much charge? I'll just do it on the whiteboard. I think that'll be clear.
3 into 1.6 into 10 raised to minus 19.
Like there's a particular value that will help you convert the number of
3 into N into F. So 3 into 96500.
Yeah. So Al3 plus getting converted to Al. So you need 3 electrons for this. So to get 1 mole of Al, you need 3 moles of electron. That is basically equal to 3F coulombs of charge, right? So 1 mole of aluminium matlab 27 grams of aluminium ke liye you need 3F coulombs of charge. The question is asking, you want to get 50 grams of aluminum. So 50 grams के लिए कितना charge चाहिए?
X.
So how will you find that X?
Oh, unitary method, 15 to 3 by 27.
Yes, 3F. Like
3F, sorry.
Yeah.
Yeah.
Into 50 divided by 27. So these many coulombs of charge is required. Okay. Now coming back to the next part of the question, you are sending 105 amperes of current, which means that you are giving 105 coulombs in 1 second. But you need these many coulombs. So in order to get
So
these,
you'll
how much?
so we'll substitute these values in the formula.
Yeah.
So T is equals to Q by I.
Correct.
So 3F into 50 by 27
Hmm.
into 105. Yeah.
So F ki jagah multiply this by what, 96500.
96500.
Then solve this, you'll get the value in seconds.
Yes, ma'am.
If you see the option is given in hours, so convert the seconds into hours. So this is basically how you approach electrolysis wala question. Your first step is to figure out what is the electrons that are being exchanged.
So N.
Yeah, you need to figure out the N. So N, how many ever electrons are being exchanged, like required, how many ever electrons are required for the reduction. That based on that, you can figure out how much charge is required. And then you can relate the charge with the current. So some questions will give you the time, like if we want 1 mole of permanganate to be reduced in 1 hour, then what current should you pass through it? Or if you want this much quantity of a metal in 10 minutes, then how much current is to be passed? Or in other cases, you'll be asked the other way around, where the current is fixed and you'll be asked for how much time will it take to do it. But essentially, the main thing is you need to identify N correctly, and based on that you'll get Q, and then use the relation Q equal to IT to figure out whatever is the unknown quantity. Okay, so all of electrolysis.
Yes, ma'am, got it.
We look at another problem, 69. In this case, they're asking for charge directly. The charge required for reducing 1 mole of MnO4 plus to Mn2 pluses. So this is not even going up to the current wala stage. You directly need to figure out how much charge. Charge ke liye you need to figure out the N first. MnO4 to Mn2 plus. How many electrons are required for this reduction? You need to figure that out. Okay.
So here we'll find the oxidation number of Mn plus, right? I mean Mn in that. Okay.
Correct. So LHS may, this is the ion, RHS may, this is the ion. So what is the difference in the number of electrons? And Shantanu, you guys following? Are you solving this question? You guys have.
Ma'am, oxidation state is +7. So +7 to Mn2 plus. So that's 5 electrons.
Yeah.
Addition.
Yeah. So 5 electrons corresponds to how much charge?
5 into N of 5F.
Calculated 5 into F is 96500.
Ma'am, but can we substitute that later in the formula?
This is the last step, no? Yeah.
Oh, okay.
I mean, you need to find out the charge. This is the only thing you need to do here. But yeah, as you said, like you can substitute it in the end. Like the previous one also, I kept F as
the calculation was much easier at the end if we substituted in the end. That was the thing.
Keep that as a rule. Like I keep advising even for math, like grade 10. Try to avoid calculations as much as possible. Keep it to the end because they get cancelled out.
482500 coulomb.
4.825 D answer.
Yeah.
So this is what your like electrolysis based questions are going to be like.
Yeah, now it seems much easier than I first read it.
So I told you like 50%.
Once you start understanding it, no, it seems easier. But till you don't understand it, it seems like, what the hell are we doing? I don't know.
It's just stoichiometry, and you're applying it to electricity instead of the concentrations. That's only it.
612.
1.5 amperes flows for 3 hours. This is like even more direct. It's more like a physics question. Oh, they're asking how many electrons would flow through the wire. Okay. So this is the ulta conversion. So
Yeah, so we'll substitute, we'll have to find Q first, and then we'll have to divide it by 96500.
So that will give you the number of moles of electrons. That again, you need to convert to number of electrons by multiplying with.
So 6 into 10, 6 into 0.2 into 10 raised to 23.
73 is again the same thing, just like you have to do it thrice. You have 5 Faradays pass through these 3 electrolytes. How much is liberated? Yeah, so directly given, so 5F. So based on that, how much of NO, how much of Cu, how much of Fe. Okay. So you guys will be able to practice this, right? Okay, next week.
Yes, ma'am.
We don't have a chemistry class. So what you can do is by Friday or Saturday evening, you can inform how's it going, whether you were able to solve or if more practice is needed. So based on that, we can figure out a class on Sunday.
Could you just remind
ma'am.
us on like Thursday